So besides just proving equality statements with induction, we can also prove inequalities. Now, as a fair bit of warning, inequality proofs with induction are sometimes some of the most difficult proofs because we're going to be pulling out almost seemingly random facts to help us be able to get to our desired conclusion. But seeing some examples will hopefully give you some insight of what are some of these random things that we can pull in and what is some of the thought process of how do we get to our end result. Okay, so we take a look at this statement. We like to prove that n is less than 2 to the n for all natural numbers. So again, convince yourself that this is true, right? 1 is less than 2 to the first, 2 is less than 2 squared, 3 is less than 2 cubed, and so on and so forth. So if we think about this proof, so if we're going to do this proof by induction, first step, we need is the base case. So we have our base case. Smallest value of n is n equals 1. So at n equal 1, we see that 1 is less than 2 to the first. So the base case is true. 1 is less than 2. Great. We are done with the base case. So now if we go on to the induction step, notice, so I am actually writing base case and induction step. This isn't just because I'm trying to teach you how to do this. This is the really good way to be able to structure your proofs. So that way it is very clear to the reader when are you transitioning from this first step in induction proofs to the second step in induction proofs. All right, so again, the induction step, we start out with our induction hypothesis. So we want to assume that this is true for n. So assume the statement n is less than 2 to the n is true for n. So assume that the statement is true for n. We'll show the statement is true for n plus 1. Now, just to have you, again, build some insight of what does this mean, again, for the statement to be true for n plus 1, what we're trying to show is that n plus 1 is less than 2 to the n plus 1. So this is what it means to prove that our statement is true for n plus 1. So we're trying to get to this step here. All right, so I might actually, right now, just going to kind of keep this here. So we can reference back to this. Now, this is something you do on the side of your paper. Maybe I'll do this over here. N plus 1 is less than 2 to the n plus 1. So to just kind of keep your goal in mind, this is what we're trying to get at. Okay, so how can we get there? So by the induction hypothesis, we see that n plus 1, okay, so we know that n is less than 2 to the n. So if I add 1 to both sides of this, well, 2n plus 1 is less than 2 to the n plus 1. Now, obviously, don't be swayed. N plus 1 is in the exponent. Plus 1 is on the bottom. Very different things. All right. So by the induction hypothesis, we see n plus 1 is less than 2 to the n by adding 1 to both sides. Okay, now we have to come up with some strategy of how can I show that 2 to the n plus 1 is less than this. So I'm trying to show that n plus 1 is less than 2 to the n plus 1 is less than a whole bunch of things until I get to this. Okay. So to help us with this, maybe it'd be helpful to look at how could I rewrite this in different ways. So this 2 to the n plus 1, that's also the same thing as 2 to the n times 2. Now that's helpful because I have a 2 to the n here, and I have a 2 to the n here. So instead of adding 1, I want to try to figure out why is it that when I multiply this by 2, that's bigger than when I add 1. So we need to have very clear steps here, because I don't want you to just simply say, well, this is obviously less than 2 times 2 to the n. We don't want to do that. We want to do short, kind of clear steps. So then we know that 2 to the n plus 1 is less than 2 to the n plus 2. All right. Hopefully we all agree upon that, right? Now, since n is greater than or equal to 1, we see that 2 is going to be less than or equal to 2 to the n. Now we have some interesting things here. So when n is larger than or equal to 1, we know that if we take powers of 2, that's going to be larger than just 2 to the first, right? We're basically saying 2 to the first is going to be less than or equal to 2 to the n for any n greater than or equal to 1. So therefore, 2 to the n plus 2 is less than or equal to 2 to the n plus 2 to the n. Now, when you add this together, we really are adding coefficients and keeping this term together. So this is now equal to 2 times 2 to the n. But we know that's exactly what we have over there, which is equal to 2 to the n plus 1. So now we keep the bases and add the exponents. Hence, we have shown that n plus 1 is less than 2 to the n plus 1. So by induction, n is less than 2 to the n for all n in the natural numbers. And that concludes our proof. Okay, so if we think about the logic of what's taking place, I've shown that n plus 1 is less than 2 to the n plus 1. Again, we use our induction hypothesis by adding 1. Then 2 to the n plus 1, this is less than this. So I've shown that n plus 1 is less than this. This is now less than or equal to this, which is equal to that. So if you have this whole string of these, we have n plus 1 is less than 2 to the n plus 1, which is less than 2 to the n plus 2, which is less than or equal to 2 to the n plus 2 to the n, which is equal to 2 to the n plus 1. So indeed, you follow the logic of these strings, and you have n plus 1 is now less than 2 to the n plus 1. So that's the goal with inequalities and induction, is to figure out how do you get this string. Now, one thing you might be confused about, there was a step here that I technically didn't need to do. So if we look at this, this is also true if I include 0. So if I take the natural numbers union the set containing 0, so if I union this with set containing 0, I would change my base case to n equals 0. I could change this to 0 is less than this. I assume this is true. And now what makes sense to do here is I don't even need this step. So since n is greater than or equal to 0, 1 is going to be less than or equal to 2 to the n. And so I have this statement here, and 2 to the n, this, great. So I could have done this for n equals 0. Now, also what that means is even for n equals 1, the statement's still true. So you didn't need to do this plus 2. It just helps you maybe start to think about how did you get powers of 2 involved. But there's obviously small tweaks that you can do where logically this is still true. You can include this, but we didn't need to include 0 because that's not what we were trying to prove. But again, hopefully this example makes sense.